Welcome to week 4 of our course. My name is Jose Rueda Torres. This week, we learn about probabilistic power flow calculation. In short, probabilistic power flow evaluates power system behavior under uncertainty by modeling inputs like loads and generation as random variables, producing probabilistic outputs like distributions of voltages and power transfers. Instead of single deterministic values, like an operational snapshot of the system when operating at a peak demand. So, to begin, let's get insight on uncertainty modeling for power system analysis. In this lecture, we learn about the sources of uncertainty in modern power systems, as well as widely used classifications and definitions. Uncertainties are everywhere across the different subsystems and components of modern power systems. For instance, the resistance of a transmission branch varies with temperature, and so weather conditions can affect the load demand at certain points in the system. Weather conditions also affect wind and solar power generation. Also, loads get connected and disconnected at any time. Think also of the reliability of each component. For instance, instead of working with 10 generators, the system might be suddenly working with 9 generators due to a failure. Less frequently, but still possible, the system could also have changes in the network topology itself. In probabilistic power flow, input data can be categorized based on the relationship between confidence degree and uncertainty level, which guides both how data is interpreted and which analysis method is appropriate. When confidence is very high, like close to 100%, and uncertainty is negligible, the data is considered as certain. In this case, deterministic power flow approach is sufficient, as inputs are treated as fixed and reliable values. When confidence remains relatively high but uncertainty is present and quantifiable, the data is treated as random, typically described by probabilistic distribution functions. This leads to the use of stochastic probabilistic power flow methods, which capture variability in power system behavior. It is worth recalling that the lecture focuses on these types of modeling and analysis. For moderate confidence and uncertainty, where data is partly random but also imprecise, a stochastic fuzzy approach is appropriate. Finally, when confidence is low and uncertainty is high, often due to vague or incomplete information, the data is considered as fuzzy, and fuzzy power flow methods are used to model this lack of precise knowledge. Let's now revise definitions of interest for this lecture. A probabilistic model represents uncertain inputs, for instance, data concerned with random variations of demand and generation, using probability distribution functions defined over a sample space, producing outputs that are also probabilistic, like voltage, current, dispatch, power transfer, or losses in the distribution or transmission network. Impact functions quantify how system performance is affected by these uncertain outcomes, such as, for instance, voltage deviations or transmission branch overloads. Probabilistic quantities of interest summarize results, including the expected value, that is the average outcome, and risk metrics, typically defined as the product of the probability of an event and its associated impact. A discrete probability function assigns probabilities to specific distinct values of a random variable, like discrete load demand levels or discrete set points of controllable devices. A continuous probability distribution function describes the likelihood of a variable taking values within a continuous range. Using a probability density function, abbreviated as PDF, where probabilities are obtained over intervals. A cumulative distribution function, abbreviated as CDF, gives the probability that a random variable is less than or equal to a given value, providing an accumulated measure of likelihood across the range. To characterize the evolution of uncertainty, the so-called stochastic models are widely used. The mean reverting stochastic process is very popular. Other options include Poisson-Gaussian processes. Let's consider, for instance, the evolution trends of load growth, gas price, coal price, and oil price. Since it is not possible to predict any of the evolution paths with 100% certainty, a set of variable evolutions for each of these parameters is generated. To get the annual distributions associated with the stochastic evolution of these trends, it's just to assume that for any given year, a probabilistic distribution function can be chosen to represent the random input data of that year. For instance, a normal distribution function can be used as shown in red in the figure. Of course, statistical tests must be done to prove these models. Furthermore, certain variables like political instability will affect prices, like oil price. But these need different types of models to consider jumps into the predicted oil price evolution trend. This is why a log-normal probability distribution function is enough for such a model. Keep in mind, though, that the emergence of more and more consumers who produce and sell energy as well, for example, from a solar photovoltaic system. This creates more uncertainty. Because of these consumers, producers, or prosumers, this variation pattern of the load demand, for example, becomes more stochastic and a single fit of a function might not satisfy. This is when the Gaussian mixture model could be a choice. This model is basically a mixture of single Gaussians, where each probabilistic distribution function is weighted by a factor. The model is described in the next video. To sum up, in this video, you have learned that uncertainties are a major challenge in studying the variable behavior of power systems, and that stochastic processes and probabilistic models are used to help characterizing the evolution trends of the parameters of interest.